Good morning, everyone. It is a great pleasure to have this conference for the students. Thanks to Dr. Soliman, thanks to Dr. Ebenhak for organizing this conference. This morning's panel session is on renewable energy and sequestration. My name is Ganesh Thakur. I'm with the University of Houston. And this morning, we are blessed with three great panelists. Dr. Martin Blunt from the Royal Academy of Engineering and the Imperial College of London. Dr. Christine Economides with the National Academy of Engineering and the University of Houston. And Dr. Rehab Elmaghrabi from the Suez University, American University in Cairo. And they will be discussing these topics as shown on the slides. The panel session will focus on the climate change mitigation, subsurface CO2 storage, hydrogen storage, and enhanced geothermal systems. We will also see a very good example of the engineered heat exchanger using fractured horizontal wells. And we'll see several examples, several ideas relating to managing the subsurface and how petroleum engineers can play a vital role in helping the environment. So with that much introduction about the subject, I would like to request our panelists to give a 5-10 minute presentation. Then after the presentations, we will open the forum or the panel session for discussions and questions and answers. So Dr. Martin Blunt with the Imperial College of London will initiate the presentation. So Martin, please go ahead with your presentation.
Well, thank you very much. And I'm absolutely delighted to be here for this panel session. So I'm going to start by looking at the potential of sequestration, essentially looking at underground fluid flow and its role in the energy transition. So you can see a graph there on the slide. What it's showing is different scenarios, so starting from now, of where we might head in terms of CO2 storage. So collecting carbon dioxide from large point sources, fossil fuel burning power stations and heavy industry, and injecting it deep underground. And what you notice here is, depending on the different scenarios in which we avoid dangerous climate change, we're looking at somewhere between 10 and 30 gigatons of CO2 stored every year by around 2050. And that, in terms of fluid volumes, is an industry that's basically of the same global scope and size as the current oil and gas industry, if not even larger. Just to put that in perspective, current CO2 emissions are around 35 gigatons per year. So it's not the only thing, it's not going to solve the net zero challenge, but CO2 storage is clearly a key contributor to achieving that. The other technology related to the energy transition is a move towards a hydrogen economy. We essentially use hydrogen as the vector to store energy in the same way as in our current energy system we use oil and gas. Again, how do we store hydrogen? We store hydrogen in the subsurface. So again, that's a problem not like CO2, where we put the CO2 underground, either in saline aquifers or depleted oil and gas fields, and we want the CO2 to stay there permanently. With hydrogen storage, we want to put the hydrogen in the subsurface and then periodically extract it and store it, extract it and store it. And of course, there are other technologies associated with flow in porous media that, again, associated with the energy transition, groundwater use and geothermal energy that our other panelists are going to touch upon. So all of this is about managing the subsurface. In oil and gas production, we've been doing this for well over a century, injecting fluids, producing oil and gas, understanding what happens underground. And that still has a key role in our move towards net zero. So if we go to the second slide, please. So I'm simply going to introduce some of the work that we do at Imperial College in understanding this. And our research and our teaching is very much around the fundamentals of flow in porous media. So we have fluids in the pore space of sedimentary rock. The fundamental physics and chemistry and flow processes occur at the micron scale of these pore spaces. So we try and understand what's going on by using X-rays to see inside porous rock, and we reproduce in the laboratory the conditions of high temperature and pressure that we'd see deep in the subsurface. So what you're seeing on the right is an X-ray microscope with a small piece of rock around 10 millimeters in diameter and a few centimeters long, where we're imaging in 3 dimensions the pore space and the fluids within the pore space at micron resolution. And what you're seeing on the left is carbon dioxide trapped within the pore space of a sandstone, and the different colors represent blobs of CO2 surrounded by water. And what this represents is we inject CO2 into the subsurface, we want to make sure that it stays there securely. As the CO2 moves, it's replaced by water, and the water surrounds the carbon dioxide. So there's a lot of CO2 in the pore space, but that CO2 is not moving. Over long time scales, it may dissolve and sink into the subsurface. It may react, but that CO2 is not going to be released back into the atmosphere. And so that's safe storage. So we try and understand from the fundamentals all the way up to modeling at the field scale how we would design and understand the safe storage of CO2 and also for hydrogen. So I think with that, I'll finish, and of course, welcome to take any questions at the end of this session. Thank you very much.
Thank you, Dr. Blunt, for a very nice presentation, and we'll be coming back to you, sir, with question and answer later on. Dr. Christine?
Thanks very much. Martin and I collaborated way back in the 90s, and since then, not so much, just here and there communication. So how lucky to be on a panel with Martin Blunt today. I'll keep my remarks quite short. I apologize for the acronyms on this slide, so let's spell them out. EGS is Enhanced Geothermal System. CCS, Carbon Capture and Storage. So let's see if we can put these two together. Next slide, please. So EGS is decades old idea. At least in the 70s, I was aware of this concept. Please go back. And so up on the upper left, we see pretty much the decades old concept. If we can find hot rock that is fractured, but not necessarily porous, doesn't necessarily contain any fluids, then the idea would be to inject a cold working fluid into this fracture system. It would flow through the fractures, picking heat from the rock, and we produce other wells to the surface, and by circulating the hot fluid through a power plant, we can generate electricity. So it's possible, but has not been very successful, that even you don't have to find the fractured rock, but just find the hot rock and then create a fracture system through which we can generate this flow. The problem has been generating a fracture system that is performant and doesn't short circuit too quickly, because if the fluids flow from the cold injection to the producers without enough residence time in the rock, then the fluid going to the power plant is not sufficiently hot. And the idea isn't working the way it's intended to work. Now we can find hot rock anywhere. We can drill right where I'm sitting, and about 23 or 24,000 feet down, we will find on the order of 300 degrees C, because we have a geothermal gradient in the earth. So the question is, at least in our mind, is how can you create a fracture system that is more reliable? And so the picture that you see at the bottom of this slide is our idea of how that would be done. And the thing is, we are using technology that is used today in thousands of wells in North America. So if we look first at the blue horizontal well in the diagram that you see there, that's the well we would propose you drill first. And then we create the hydraulic fractures from a horizontal well without any particular layering effect. Those very well may be radial fractures like what have been diagrammed there. So we do that, which is already a known technology, except for doing it in very high temperatures. Currently, I think the industry is at around 200 C, not 300 C. Then we would propose you drill the red wells to intersect those created fractures, and that creates a circulation environment, which would make up what we would call an engineered heat exchanger. So basically, we are using the multiple transverse fracture horizontal well technology to achieve this system. We just did a paper on this, SPE 205967. You should be able to find that for more information on this system. And my master's student, Leila Denali, did a lot of modeling. The last thing I should say about the diagram is there would be many more fractures, and the wells are longer than what you see there. So this would be sort of the heel section of what we're talking about. So if we can go to the next slide. Now I need you to follow what this picture is trying to show. So in Canada, they already drill very much like what we see here. So we're looking at a map view into the earth of, we've got, what are we, I think we've got 12 wells there. So each of the curved black lines coming from the well pad, they're going into a shale gas formation. And the little lines that look vertical in this picture are the hydraulic fractures. And so, for example, the Horn River development looks very much like what this picture looks like. And Horn River, Haynesville, Eagle Ford, Marcellus are all examples of shale gas developments, and they are all on the order of 150 degrees C or a bit higher, which is just at the bottom of what is considered low-grade geothermal. So let's try something here. If you'll click the slide, we'll get an animation. So next slide, please. Okay, so we're just going to drill injection wells. And the idea is that these will intersect the fractures that are already there. So where would we do this? We need depleted wells. So when the gas is no longer producing, we still have the hot rock. So drill the injection wells to create the circulation like what I pictured in the previous slide. And if we'll click just once more, there's a little something more to say. A very interesting idea that Karsten Preuss and others have written about is using CO2 as the working fluid. They suggest that the properties, expansion with temperature and compressibility of the CO2 may mean that it's self-circulating. So our circulation is deep in the earth. We need to get production back to the surface. And CO2, unlike water, might do this without any pumps or compressors. Also, it looks like CO2 might be better than water in another respect, because there is concern with systems like this. Will they short circuit and will some of the fractures get all of the fluid instead of getting the working fluid distributed all the way down the length of the horizontal wells? Well, the thing is that CO2, even in a supercritical form, is gas-like, and so it may exhibit non-Darcy flow characteristics that would make it self-allocating. And the last interesting point that Price also mentioned is about the storage. That expected leakage of the CO2 into the formation would serve as a permanent CO2 storage mechanism. So I'll stop there. I hope I didn't overstay my time, but it's a very, very interesting concept.
Thank you, Christine. And we will go ahead with next with Dr. Rehab Elmaghrabi. Go ahead, please.
Thank you. So today we are going to continue talking about CO2 sequestration and hydrogen production and the storage, actually. So it can be considered as the bridge between the cleaner energy and the petroleum engineering. So if you just click on the slide. So for petroleum engineering, when it intersecting with renewable energy or a clean energy production, they can be, if you can click please on the slide.
I'm on the slide. It's okay. Very good. Thank you.
Yeah. Okay. So you can find that the intersection between, or the connection between the petroleum engineering specialty and renewable energy or cleaner energy production. We can see it in the CO2 sequestration and the hydrogen storage for now. Maybe later will be some new connections. Next, please. So for CO2 sequestration, the idea for CO2 sequestration, or the goal for CO2 sequestration was to keep our environment, cleaner environment, to stop climate change and the greenhouse gas effect that is was due to the CO2 emissions to the atmosphere. We know that the COP26 is currently running, and the goals, they emphasize the goals that they reached in the Paris Agreement, that they have to keep the degrees, the amount of temperature, or the increasing in temperature in our, for pre-industrial, from the industrial revolution until now, to be lower than 2 degrees Celsius. Actually, we are reaching now between 0.8 degrees Celsius increase in the temperature up to 1.1 degrees Celsius increase, and this is and we are still increasing, have monitored increase in the temperature of our climate. Actually, also they would like to keep net zero emissions with no emissions from fossil-based fuel or any fuel activities or any energy activities. So it will reach net zero in the second half of the century, like it is 2050. Okay. So to reach this, while we have still dependent on fossil fuel with more energy, energy burning and consumption of energy. So how can we reach this goal? The CO2 sequestration is one of the way to reach this goal. So CO2 sequestration is just a CO2 cannot maybe not utilize. One of the way to do CO2 or to utilize CO2 is to inject CO2 in the underground aquifer or for the or current oil reservoir, actually for enhanced oil recovery. So I can now utilize CO2 for enhanced oil recovery. So this is one of the link between petroleum engineering. So we can produce more fossil fuel. It will be feasible to inject CO2 in the underground because it is costly. So because you are producing fossil fuel or oil from this injection of CO2, so you are getting more money from it. The other way is just to inject CO2 because of the environmental limits in depleted oil reservoir or in aquifers. One of the things that you can utilize CO2 is to do chemicals, is to convert this CO2 to chemical. But actually, CO2 is not a very reactive gas. You can say it's not active one, so it is harder to get to make CO2 to react, but it can be done because using catalyst and the high temperature, you can convert CO2 to methanol and methyl ether and some other chemicals. Actually, there is current research doing so. So for CO2 utilization or for CO2 sequestration, CO2 is just injected in the underground just for the sake of CO2 injection without reaction with anything, just without the production of anything. It will be injected on 1 kilometer aquifers, in a water aquifers, without reacting. CO2 can react actually with carbonate rock. So if CO2 is injected in sandstone rock, so there will be limited type of reaction in this sandstone rock, but in aquifer, in carbonate type rocks, there will be a reaction with the carbonate, but up to a certain limit actually. CO2 can be injected or can be stored in the underground using different mechanisms like the solubility, because CO2 is soluble in the water, so CO2 will dissolve in the water, which is not the case with hydrogen. So if you are going to store hydrogen is not soluble actually in water, and CO2 also can be stored trapped forever, residual trapping, and some other mechanisms. So the next slide, please. Okay. The next thing is the hydrogen production. Because we want to reach to a cleaner environment, we want to limit the increase in the temperature that we are currently facing. One of the direction is to utilize renewable energy for the production of hydrogen. So why hydrogen are being used? Because hydrogen is a clean fuel. So if you are going to use hydrogen, there will be no CO2 emission. But not everything is as shiny as it looks. So to produce hydrogen, we have three ways. Actually, until now, 3 ways, common ways that we can see. There's different colors of hydrogen, but this is the common one. So the green hydrogen, the gray hydrogen, where we already know this, it is a methane, the steam reforming of methane. So methane will react with oxygen to produce syngas. So carbon monoxide and the hydrogen mixture are produced. This syngas is converted later to carbon dioxide, and this carbon dioxide is allowed to the atmosphere. So in this case, green hydrogen is not a clean energy. Gray hydrogen is not a clean way of utilizing our energy, because we have CO2 emission. Again, it is contributing to our the increasing the level of CO2 and to the global warming. So this is moved us to the idea of blue hydrogen. So in this case, this CO2 that was produced or co-produced with the hydrogen can be utilized. Now it is CO2 storage can be one of the solutions for this. So to reach a blue hydrogen, we can get this CO2, capture this CO2, co-produced with hydrogen, and also produced from using the energy, or the furnace and the oven that giving us heat for this reaction. There is CO2 emissions also from the flue gas. So we can capture this CO2 from the flue gas and CO2 from co-produced with hydrogen and store it using CO2 sequestration forever. So now it will be a cleaner hydrogen. So, but we are using fossil fuel for this, so it is blue hydrogen. Again, one of the more trendy concept is the green hydrogen. For the green hydrogen, we are using hydrolysis. So we are using water to splitting of the water. So electrodes, so the water H2O will be split to hydrogen and oxygen. To do this, we need energy. Of course, we want a green hydrogen, so we cannot use fossil-based fuel to get this energy. So now we are using renewable energy. The most common source of renewable energy that we can use is solar energy and wind energy. But because wind energy and solar energy is not available or commonly available all the day, all the year round, so of course you can produce hydrogen, green hydrogen, with no CO2 emission, or co-produce with the hydrogen, but we cannot get a stable hydrogen production. So the concept of hydrogen storage we get from this way. So to get a supply, why not store hydrogen in the underground gas reservoir? Because you already have natural gas in gas reservoirs. So it is designed for it. It is naturally designed to accommodate gas. Of course, the hydrogen molecule is very smaller, but it may be more studies is needed. But it can do. So it is feasible idea. Why not try it? So so hydrogen will be stored in the underground for continuous production to like ensure continuous production of hydrogen. Of course, this idea has a pros and cons. So one of the pros, you will have a continuous production of hydrogen. You will secure supply of your supply of energy. But to keep short, for the cons, the hydrogen is very flammable gas. Actually, have lower and higher ignition point. Flammability limit is a higher flammability limit. Actually, it can be explosive. So so it has to be handled with care. It is not reactive with the reservoir, but with the carbonate and the sandstone reservoir compared to CO2, which is a reactive one. But hydrogen is not reactive. But how to monitor the emission of hydrogen from this reservoir need more modeling and more experiment. And as just Professor Martin has outlined or talked about this. So thank you, and hope that it's not very long.
Thank you, Dr. Rehab. No, it was just perfect with the three panelists. Now we will get involved with a Q&A session, and some of our volunteers are helping us with Q&A session. In the meantime, I would like to get started with a question for Martin. Martin, you pointed out CCS alone will create an industry even larger than the current oil and gas industry. Could you kindly elaborate on that? Because this is very exciting for the students to hear this.
Yes, I mean, this is the potential if carbon capture and storage is used to capture a significant fraction of our current CO2 emissions. And it comes simply from looking at the volumes of fluid involved, right? It's simply, you look at the volume of oil and gas that's produced, right? We will be injecting at least that volume in the subsurface under some of those scenarios that I outlined in my presentation. In addition, there's the generation of carbon-free power, as my colleague Christine noted, with geothermal energy, and of course there's the storage of hydrogen. So no, there's an enormous potential, and I would like also just to take this opportunity to say how delighted I am to be in the panel with both Christine and Rehab, both of whom I have worked with for many years. So I'm sure they have something to contribute, a lot to contribute to all of these questions as well, of course.
Great. We would like to hear a few questions from the audience. So Ahmad and the volunteers, could you kindly help us? with some
Yes.
of the
Mariam,
questions.
are you ready? You can go
Yes,
ahead.
we actually have some questions. So the first question is that regarding CO2 injection, what are the main challenges related to surface facilities?
Great question. Martin, Rehab, Christine, would you like to address that? If you don't feel comfortable, I will be glad to address this. So go ahead. Go ahead, please. Martin, your chance first. And
Okay, I mean,
yeah.
I think we have lots of experience with CO2 injection for enhanced oil recovery. So there isn't a unique challenge. The principal challenge with injection is to make sure that you don't fracture the formation, because that could lead to potential leakage of the CO2. So it's really the pressure monitoring, but there's nothing, again, it's using the same skills and experience in the oil industry.
Fantastic. Very good answer. I have been working with CO2 flooding, CO2 EOR for over 40 years in the Permian Basin until I retired from Chevron a few years ago. And we started our first CO2 injection project there in 1972, the SACROC project. And actually, it was the first anthropogenic CO2 injection in the world and the first commercial scale CO2 EOR project in the world. There are practically not much difficulties with the surface facilities. CO2, even mixed with a little bit of water, is a carbonic acid. So corrosion and scale, you have to watch. You have to design your equipment reasonably in a careful way. But as Martin pointed out, one of the things that we made sure that we never went above the fracturing pressure or the original reservoir pressure in the reservoirs, so that we did not create any kind of additional communication out of the reservoir. So pressure monitoring, injection profile control were the two most important things for the surveillance and monitoring of the CO2 EOR injection projects. Today, there are over 136 CO2 EOR projects just in the US. And I would say almost all of them are economically and environmentally very successful. Any other questions, please?
Yes.
Comment to, oh, okay, never mind.
Go ahead, please. Please go ahead.
Go ahead, I would like to add a comment to that.
Yes, go ahead, ma'am.
Thank you. I think the harder issue for the CO2 EOR and the CCS and the geothermal that I talked about by far is the capture, not the injection. It is very expensive to capture CO2. And I have recently understood that the sources for decades of Permian Basin CO2 are actually depleting. And if that is going to continue, we really will need anthropogenic CO2. And I would just like to connect finally with Rehab's comments about the blue hydrogen, because blue hydrogen from methane is one of the most cost-effective sources for CO2 capture. And so it makes blue hydrogen an extraordinarily attractive concept, and one that I personally see as an important factor in the future for petroleum engineers.
Great. Thank you. Next question, please. From the audience. Yeah.
Yes. What do you think about the in situ hydrogen production from petroleum reservoirs using in situ combustion?
Anyone would like to address this question? Dr. Rehab, Dr. Christine, Dr. Martin?
I don't think it's exactly in situ combustion, but I have been following this a little bit. The idea of getting hydrogen from the heavy oil in Canada. So it's not exactly a combustion process, but it's one that I have my eye on. So I'm glad that we had a question on that.
Yeah, I think it's very promising as a concept, whether or not how much of a reality we can make of it, but as a concept, it's amazing, right? Rather than extract hot, high pressure fluids to the subsurface, let them cool down, then refine them and burn them and let the CO2 go into the atmosphere, create basically at the wellhead, the final product that you want.
Great. So conceptually, a great idea. Implementation requires a lot of efforts, no doubt about it. In the meantime, while we are waiting on some questions, Dr. Rehab, how petroleum engineers would play a key role in CO2 sequestration, but you mentioned in hydrogen production and storage, there are pros and cons of hydrogen storage, right? So would you like to comment on that, please?
Okay, so for as you outlined that CO2 storage, we are currently using for CO2 storage and also for hydrogen storage, we are expecting to use the current depleted oil reservoirs. So petroleum engineering with their expertise already know every bit about this oil reservoir. Also for the aquifers, but not for hydrogen storage, aquifers for CO2 sequestration, they can utilize their expertise into drilling and in exploration and for injection of the CO2 and also for the production. So they can utilize their expertise in this field. So for hydrogen sequestration actually is a field of petroleum engineering. Hydrogen storage actually for the pros and cons, there is different for the hydrogen is not very active also, but it reacts with it can enter in reaction with the microbe reactions. This is not like a well understood area how this will be how hydrogen will deal with this. Okay, there is high salinity, there is high temperature, but actually how this is going to take us need more studies. Hydrogen does not react with sandstone or carbonate rock, so it is something good. But regarding the cons about this, with hydrogen, what is the production rate after we store hydrogen? What is the production rate of this hydrogen after we store it? What is the amount of hydrogen that we are getting from this stored amount of hydrogen after? Because there will be some trapping may occur. So this is some of the points. Actually, there is a long list, but here's some of the points about hydrogen storage. Actually,
there was a question from the chat that I picked up, and the question is, which is the largest working company for the CO2 storage at this point in time around the world that is being implemented? One of the panelists, would you like
Martin,
to?
I think. No, not myself. It's Martin. I think he will be the one to answer.
I mean, I don't want to say who's the largest, but many of the major oil companies are seriously involved in CO2 storage projects. Obviously, the first was Statoil, now Equinor, with a Sleipner storage site underneath the Norwegian North Sea. That started in 1996, essentially separating out carbon dioxide from a natural gas field. Rather than releasing in the atmosphere and paying a carbon tax, it's been injected in the subsurface, and 25 million tons of CO2 has been safely stored to date. But certainly Total, BP and Shell are also actively involved in major CCS projects.
Great. I would like to add to that, Martin, Chevron's Gorgon project in Australia that has been injecting about 3.5 to 4 million tons of CO2 per year. And their target is to inject over 100 million tons over the life of the project. The project has been going on successfully for many years. At the point in time when the project started, that was the largest project for CO2 injection around the world. that contained 9 CO2 injection wells, 4 water production wells, and 2 water injection wells. And what they were doing, producing the CO2 with the gas mixture, separating that CO2, injecting into a separate formation, aquifer, and producing the water from the aquifer so that the aquifer pressure was maintained. And they had observation wells, they had seismic monitoring. So this is also one of very important project called the Gorgon project in Australia. Thank you. Any other questions from the audience, please?
Yes. What are the long-term effects of CO2 storage?
What are the long-term effects of CO2 storage? For the CO2 EOR projects, they have been going on for over 40 years in the Permian Basin. Practically, there is no negative effects that we have seen, that we have experienced. And the key to that is surveillance and monitoring, and key to that is reservoir management. And key to that is how do we manage the subsurface? That is the key. If we continue to manage the subsurface, and in my opinion, in our opinion, there is nobody better equipped to do that than the petroleum engineers, the petroleum geoscientists, who can do that monitoring. And as long as we monitor those carefully, as long as we follow the principles of reservoir science, we are in good shape. Thank you. Any other question, please?
I think that we should elaborate a little bit on that, and Martin would be the better person to do it. But Martin, maybe describe a little bit about what we expect CO2 will do over a 100-year, 1,000-year time frame.
Yeah. I mean, this for petroleum engineers, we're used to stuff being underground for geological times, but I think for the wider public and governments, it needs to be explained that when you inject the CO2, the major concern is pressure, the buildup of pressure, but you can monitor that and you can deal with it. Over time, the CO2 gets more securely stored in the subsurface. So over time, as it migrates, as I showed in my picture, it gets trapped essentially as pore space bubbles, and so it no longer moves. Its migration of the CO2 that's connected becomes slower and slower. It gets trapped underneath low permeability layers under caprock. The CO2 can also dissolve in brine, but when it does so, the CO2-laden brine is dense, and so it sinks, so it goes down, and it may react. And we've been talking about reaction, but again, you can form solid carbonates. The point here is that it's very unlike nuclear waste storage, where you sort of know what to do for the next 10 years, but you're worried that something terrible is going to happen in thousands of years' time. CO2 storage is not, and I emphasize not like that. As long as you monitor the movement and the pressure over the relatively short term, in the long term, the CO2 will remain safely underground. And we know that because there are many natural sources of CO2 where CO2 has remained in the subsurface for millions of years.
Very good. And some of those examples are the existing CO2 reservoirs in Colorado and Wyoming, where the CO2 has been there for millions of years, or at least hundreds of thousands of years for sure. Great. Thank you, Martin. Any other questions that we have from the audience? We have time for 1 or 2 questions. More questions? Yes.
Is it economically viable to utilize CO2 for producing hydrogen energy?
Anyone like to address that? Dr. Rehab, would you like to?
How can we use CO2 to produce hydrogen? There is no connection. Carbon dioxide is the carbon and the oxygen, and hydrogen is a different element. So it cannot be used to produce hydrogen, but it can react with hydrogen to produce methane, for example, if you want. So some reactions and a different condition, so you can do this. But no. CO2, in short, CO2 cannot be used to produce hydrogen.
Great. Any other questions from the
I would
audience?
like to comment further on that.
Okay.
We're looking very closely at a tight integration for the blue hydrogen production where you collect the CO2 as you do for blue hydrogen and re-inject it into your methane or natural gas reservoir. So this is reservoir management of a new style for petroleum engineers. And it looks very, very interesting because in effect, this is enhanced gas recovery. Instead of EOR, we get to EGR. So you're asking, okay, that's methane. How do we get that to hydrogen? Well, the answer is what you heard. The produced methane is used to generate the hydrogen. So if you follow me, produce the methane, generate the hydrogen, collect the CO2, put that back into the reservoir, and thereby you're actually enhancing hydrogen through CO2, in my view.
Great. Great. One final question, please, from the audience. Go ahead.
Yes. How does it take for geothermal wells to deplete?
That's a great question. So if we're talking about the EGS, then we can model the heat transfer from the rock. And so it's basic thermodynamics that is readily understood. But if we are talking about hydrothermal, geothermal, where we find hot fluids that we can produce from pore space, then it's a little bit different because you're mining the fluids that have the heat rather than the heat directly. But there are plenty of examples of successful geothermal operations of both types because even heat pumps are mining heat from the earth in order to use for even household needs. So to answer in more detail requires much more time, but I hope this is helpful to reassure you that we understand this quite well when it comes to geothermal.
Fantastic. Thank you, Dr. Christine. I would like to thank our panelists, Dr. Martin Blunt, Dr. Christine Economides, Dr. Rehab Elmaghrabi for participating this morning and this afternoon in UK and Egypt. Thank you coming in at a late time. We had a great panel discussion, and I would like to thank again the organizing committee for a very good session and giving us an opportunity to hold this session. So the renewable energy and sequestration panel session now concludes. Thank you, panelists, and thank you for the attendees from around the world. Thank you very much. This concludes our session.
Thank you very much, everyone.